Rovers. Everybody knows them, everybody loves them. But how do they actually move from A to B? Let's look into it.
Alright, let's say we have a rover standing currently on an arbitrary point A and we want him to move to point B. On a higher level, we can just say him, okay, go to point B somehow. But there's a little problem. Let there be a rock in the middle. And now we cannot just drive straight to B. So what we need is continuous processing of our real-time environment, and we always have to wait between accomplishing our mission goal and reacting to our environment. Also, this has to be instantaneously, so we cannot do it with some humans. For example, look at the Mars, we already have over 20 minutes of go-around time for a message. Before we go too deep into the topic, let's look at a quick example. Spirit and Opportunity, launched at 2003, were designed for only 90 souls, but lasted much longer, actually over 5,000 souls. They moved with a pretty fast speed of 1 centimeter per second. It was split into two phases. First, they took around 20 seconds to evaluate their surroundings, and then they were able to move for 10 seconds. And in the case of Opportunity, we actually managed to get to a distance of over 45 kilometers. So the system we designed has to be reliant and work in the long term. We will start with the actual steering mechanism on how you can control a rover. First of all, we want to look at skid steering, which is a very basic version of steering. You all know this from tracked vehicles like Wall-E, for example. What we do here is we steer with how much we actually use what motor. So if we want to do a right turn, we give more power to the left motors and less power to the right rotors, or in extreme cases, let the left rotors roll to the front and the right rotors to the back, so we can do a turn in place. The advantage of this design is that it's very simple and that we have very high maneuverability in close corners because we can spin at one point. But, and that's a big but for our problem set, we have a high power consumption. Power is rare in rovers. We have a high wear on wheels, which is especially bad because we cannot just go there and swap a tire. We have one tire for the whole mission, so we want to reduce that as far as possible. And also we have not really precise control if we want to go on a very specific point to do a measurement, for example, on the floor. So it works. It also was used in some rovers, but there are better options. The most common option, and arguably better than skid steering, is Ackermann steering. You all know this. Why? Because it is used in cars also. What we do there is we steer by rotating some wheels. Let's look at an example. In the car we have our two wheels on an axis, and if we turn our wheel, the wheels rotate to left or to the right, and with that we can steer. This system allows us to have a common turning center. This gives us a minimal tire slip, but on rovers we have two special cases. First of all, we don't use a normal Ackermann, we use a double Ackermann. So we don't rotate one pair of wheels, we rotate two pair of wheels on front and on back. This allows for even better movement and tighter turns. And the second part, as you can obviously see in pictures of rovers, we do not have an axis to connect the wheels. This brings with it that we have to simulate something like that in software, but also gives a very big advantage that we can independently move the wheels and basically rotate around ourselves and put the center of rotation inside of our rover, like seen here. As already said, the advantages of such a method is better control and precision, way reduced wear on the tires, and very high speed turns. But as obviously seen, it's a little bit more complex in mechanical and software design, and we are a little bit limited on tight spaces. Yes, we can rotate around ourselves, but not as good as with skid steering. Now, if you want to try this out for yourself, there is a very cool NASA website where you can play around with one of their rovers and actually point and click him to a location where it wants to go. And you can see in action how the Ackerman steering works. But wait, there's more. As we all know, extraterrestrial terrain is not as flat as a street. So we actually need a mechanism to be able to always stay on the ground and not just fall over. For that, we can use something like the boogie mechanism, which is basically a suspension system with two joints where we separate some of the wheels from each other to be able to keep all of them on the ground when we go up or downhill. It enhances the stability a lot. For example, it was used in Curiosity and Perseverance, and as you can see in this animation, it works actually pretty well. With that, your rover will not just fall over when there is a small hill. Now that we know how the hardware works, let's take a closer look at the software. For that, you should know what a closed loop system is. Basically what we are doing is we take the output of our system, analyze it, and adjust our input according to the error we have in our system. This gives us better accuracy, reduces disturbances from errors, and enhances our stability. Also important to know is that we have more than one of such a system. Just for controlling our movement, we use one for our speed controller, how fast we are going, and one for our steering on where we want to steer. And also, these are not only used in locomotion, we also use them in temperature sensors and all such stuff. But this is a topic for another time. The first type of these controllers I want to look at with you is the Bang Bang controller. It was one of the first control software systems that were used. And basically what we are doing is we are switching between minimum and maximum control input. So if we are a little bit too low, we set our input to max to get it back up. And if we're a little bit too high, we set it to 0 to get our system back down. This is very efficient and very simple to implement, but has some major drawbacks for our scenario. We have a lot of wear on our components. These maximum minimum control inputs are not really good for motors or any kind of actuators if you want to run them for a long time. And today they're only used for some other subsystems like temperature measuring and no longer for locomotion. Then we have continuous control, where we always look at our output and adjust it in very small steps continuously. Hence the name. This results into a very smooth and steady movement, and we can handle very small derivations in real time since we are only doing this in very, very small steps. It has way less wear on the gears and very accurate navigation, but has the big drawback that you need a lot of computational power to compute what you want to do, and it's kind of slow in the response, so it's better but not perfect. And going one step further to the PID controller, what does that stand for? Proportional integral derivative, where we look into the past, the now and the future. We can look at the current error, where are we and where do we want to be with our output of the system. But also we can integrate over old errors to compensate errors that accumulate over time. So that's our past part. And then the third part, where we can look into, is we can predict what our error could be by considering how the rate of error changes right now. This is very precise and stable, but also even more complex and power intensive than the previous one. In the end, this is the system you want to go to for current rovers. For example, Curiosity uses this, comparing the power you need to move the wheels and the whole rover to computing the movement. The computing part is neglectable. The only important part is that you need hardware microcontrollers on board that are capable of calculating this fast enough, so you can run it in a way that you can proceed the mission. Moving to error detection and recovery. How do we even check if we have an error in our system? I mean, yes, we have our sensors and the feedback from them, and we can compare the is and the should. And with that, we can basically set up an error threshold. So we define a space where we have to be around our should, where we say, okay, this is fine, but if we go out of this threshold, we have to do something. And on the other side, what we can do too is data analysis. So we have to check if a faulty sensor exists, so the values we get from this one will be wrong forever, or if it's a problem in the controller where we can fix it software-wise, or is the actuator broken. So for example, if when one of my wheels is broken, I will never be able to move as I should. And for the controller, it's pretty easy. We basically already talked about it. We can just adjust the algorithm in the controller and we are done. And sensors, we normally can try to recalibrate. Sometimes it works, sometimes it does not. And then there's the other part where we cannot recalibrate the sensor or some of our component is stuck. That's what we call an unexpected situation. And this is the point where the autonomy of the rover stops and we actually need a human to interact with it and help to fix the problem. For that, let's look at the worst case scenario. So, what do we do if we have an unexpected failure in our system? So, for example, a stone or stuck in sand. First thing we want to do is we want to hold all the processes we are running right now and identify the problem. And with that, we request human interactions because the rover accepts that it no longer can do anything to better his own situation. And he starts collecting more and more data so people on Earth can analyze the situation as good as possible. And with that, you can start engineering model testing, so basically a replica of the rover on the Earth to simulate the situation and see what can we do to fix this and hopefully save the rover. Let's look into a worst case scenario, the Spirit rover. 2009, the rover was about 6 years on Mars at that point. The rover drove over a not so stable crater and broke into it. And in there was a lot of sand. And basically what happened, the whole rover was stuck in sand and could no longer move forward. Humans, so people from the NASA, tried to save the rover, did a lot of calculations. After 6 months, they tried the first rescue, but they could only move the rover for a few millimeters. At that point, another problem was adding to this bad situation. The Martian winter was coming, so basically less and less sunlight for the rover, less and less power to do stuff. So at one point it was decided to make the best out of the situation and use the rover as a stationary science lab to do as much science as possible in the current situation. And the last locomotion thing that was done on the rover was move him a little bit in the millimeters just to be able to have a little bit more sunlight on the solar panels to get more energy into the system to do experiments. Again, this is a worst case scenario. Normally you have a high chance to fix such problems, but in this case we only had 4 working wheels left, and we have a rover that is like 6 times as long in active duty than it was planned. So I personally still see it as a win that we can use Spirit as a stationary science platform at that point. Okay, but now to a bit more fun part. Let's talk about odometry, which basically is the science of knowing where you are without external input. On Earth that's easy because we have great inventions like the GPS that can pinpoint us to centimeters where exactly we are, but we do not have such a system on Mars or any other planets, moons, or wherever we want to send our rover next. So we need to do it in another way. The simplest solution for that is mechanical odometry, which is basically putting rotary encoders on the wheels and collecting the data on how much the wheels turned and calculating out of that where we should be. This has some major flaws like slipping in sand or not reading the data right. All that can happen. And for that, we can use visual odometry, where we take pictures from the surrounding with onboard cameras or other methods of data. For example, a LiDAR sensor would be a good indicator, and use this data fused together with the mechanical odometry to get a better idea of where exactly we are. In some cases, what you can do, a current point in the development, is actually build distributed systems where you can use a rover on the ground and a satellite in the sky together to get even better location without needing a full GPS system, but only with one satellite that takes pictures. And what we can see pretty clearly in diagrams like this one, we have a pretty good idea with mechanical odometry where we are, but it derivates a lot, especially as you can see in the rotation in which we are moving. And with visual odometry together, we can get a very specific point on where we are. And moving one step further, we can use this data we collected with odometry to build point clouds. So we can map our surroundings, where is a stone, where is a cliff, stuff like that, and save it as a 3D mesh. This has some big upsides. For example, if we ever go back into this territory, we already know where we can and can't go and can route our way through the area way more efficiently. It's also interesting for possible later landings to see where is a good surface where we can land. And also, if for some reason we lose connection and the rover is moving around, we can use this mesh to estimate our position where we are right now compared to the landmarks around us. And with that, I want to close this presentation, video, call it whatever you want. I know we couldn't go too deep into detail, but 20 minutes is still a limited time. I hope you learned something. If you have more questions, feel free to ask them. I will actually try to respond to them. And see you in the next one.